Alright, so we're starting with problem 1 here. I'm going to rapid fire through some of these, but we've got a fan is turned off and its angular speed decreases from 10 rads per second to 6.3 rads per second in 5 seconds. And we want to know what the magnitude of the angular acceleration of the fan is. So we have a kinematic equation here where we have the final angular velocity is equal to the initial angular velocity, and then all we're doing to that initial velocity is we're adding this time dependent term. So for every second that passes, we add this acceleration. So if 5 seconds pass, then we add 5 chunks of that acceleration. Alright, and so in this case we want to find the magnitude of this angular acceleration. So we can rearrange the formula for that angular acceleration. Essentially we subtract the initial angular velocity from both sides, and then we have at, and we divide by t on both sides. So we'll end up with this formula right here. The angular acceleration is equal to the final angular velocity minus the initial angular velocity over the amount of time that passes. So in this case, we have 6.3 minus 10 all divided by 5.0. And this is going to give us negative 0.74 rads per second. So this is our answer here, and we can select that right there. Alright, now number 2. We have a hoop of radius r with mass m rolling without slipping. So we have some ring on some surface, and it's going this way while rolling. And we want to know which form of kinetic energy is larger, the translational, which is this, it's just translating from the left to the right across the surface, or rotational, which is of course the spinning motion. So in this case, the translational kinetic energy we know equals 1/2 mv squared, and this is the translational. And then we have that the kinetic energy rotational is equal to 1/2 I omega squared. And so you can see here what I've mentioned a few times, that the moment of inertia is sort of the rotational analog to the mass, and obviously the rotational velocity is equal or analog to the translational velocity. But in this case, the the moment of inertia is just a very basic mr squared, and that's the most basic formulation of a moment of inertia you can have. You can have it for a point swinging on a string that is traveling around a circular path, and you can have it for this ring. This hoop has a similar shape. It creates a ring. If you have some sort of a cylindrical shape, then this spinning, into the page there will have a different moment of inertia than this, but for this case, the kinetic energy that's rotational just equals 1/2 times I, which in this case is mr squared. And we know that omega in terms of r here, or v, is v over r, so omega squared is v squared over r squared. These two r squareds will cancel here, and this equals 1/2 mv squared, which is equal to our translational kinetic energy. And because of that, we can choose option C, both are equal. Alright, number 3, we have a person pushes on a doorknob with a force of 5 newtons, and it's perpendicular to the surface of the door. The doorknob is located 0.8 meters from the axis of the hinges of the door, begins to rotate, and we want to know what the moment of inertia is. of the door about its hinges. So in this case, we can use Newton's second law with rotational form. So obviously Newton's second law in translational form is F equals ma. And for rotational, the analog to force is torque. The analog to mass is the moment of inertia. And the analog to acceleration is just the angular acceleration alpha. And in this case, we can rearrange, simply say that the moment of inertia is equal to the torque divided by the angular acceleration. And the way we can find the torque from this problem, we are given the radius, essentially, which is the distance of the force from the object that's being rotated. In this case, we have 0.8 meters. And then we have the force, which is 5 newtons. And that comes from torque equals the radius times the force. And we'll have all that over the acceleration, which is going to be 2 rads per second squared. And if we calculate this all out, then we're going to get 0.8 times 5, which is it's going to be 4 divided by 2 is 2.0 kilogram meter squared. And that is option A on our problem here. Okay, problem 3. If we look here, we have a body here that's connected by rods. It's 4 masses, and they each have the same mass m. These are arranged in the xy plane as shown, and they're connected by light sticks. A here is the distance of each of these rods to the center, and it's rotating, as notated here, around this y-axis. So obviously this one right here will just sort of be spinning in place. This one over here will follow a large circular path around the y-axis. This one right here will follow a shorter circular path, and this one will follow an identical circular path down lower on the y-axis. So the way we find the moment of inertia here, if the moment of inertia is simply m times r squared, with r being the distance of the force from the rotating body or from the axis that we're rotating around, then we can simply sum together the different moments of inertia, and that will give us here this first one right here. The distance from the axis it's rotating around is 0. So m times 0 squared is just going to be 0. So we can say 0 plus the one on the bottom here. This is a away from the y-axis. That's the radius there, and you can deduce that simply from the fact that this rod here is the same distance from the y-axis as this mass is. So the radius there is going to be a. So we can say m a squared. The mass on top is going to have the exact same moment of inertia, since it has the same distance from the y-axis. And then lastly, this one over here is twice as far from the y-axis as either of these two masses. So this will be plus m times 2a squared. All of this equals 2ma squared plus 4ma squared. And this will equal 6ma squared. Now, if the mass equals 2 kilograms and a equals 1 meter, then this equals 6 times 2, which is 12, times 1 squared, which is just 1. So we have 12 kilogram meters squared. And on our answer sheet here, or on our problem, that corresponds with answer choice B. All right, for number 5 here, we have a 300-gram mass attached to a horizontal spring with a constant of 260 Newton per meter, and it's oscillating on a frictionless horizontal surface with an amplitude of 8 centimeters. So in this case, we're going to use our formula 1/2 times Ka squared, which is a specific case of the more general spring equation, 1/2 Kx squared. In this case, we use A since the spring is stretched to its maximum length, and we consider the maximum length to be the amplitude of that spring system. So we're simply substituting A for x. So don't get confused if you ever see a formula that says 1/2 Kx squared. This one applies to more problems, but in this case, we are using this one. So as you can see, the mass is actually not even relevant. It's a red herring in this problem. You don't have to use that 300 number at all. So this is equal to the mechanical energy in the system, and we can say that's equal to 1/2 times the spring constant K, which is 260 Newton per meter, times the amplitude squared, and the amplitude here is 8 centimeter or 0.08 meters. Remember, in spatial dimension, in length, we always want to convert to meters as our base unit. And this calculation, when we plug it all in, gives us 0.83 joules, which is answer choice E. Alright, I'm going to quickly go over number 6, which we went over during our session. I'm just going to quickly go over the things that I told you so that you have it in video form here. We have the air track cart oscillating on a spring, and we're given the formula here, x equals the amplitude times the cosine of omega t, and we need to find t. So in this case, what I would do is I would divide both sides by a, and that's going to give us cosine of omega t on the right hand side and x over a on the left hand side. And then the operation we can do here to isolate this omega t is to take the inverse cosine of both sides. So we'll have the inverse cosine, which is a function on your calculator, of x over a, and that's going to be times omega t. And then, of course, if we divide both sides by omega, then we will end up with our t. So in this case, we're taking the inverse cosine of omega over a, or excuse me, x over a, which is going to give us 0.818 radians, and that's going to equal 6.35, which is our omega, and we know that because it's just written in here as omega. We're going to get that times t. So if we divide 0.18 by 6.35, then we should have our t. And when we do that, we get 0.129, and we know that our units are in seconds, and that is answer choice C. Okay, for number 7 here, I'm going to go into a little bit more detail. So we have maximum speed of a 3 kilogram object is 4 meters per second here, and the maximum acceleration of that object is 5 meters per second squared, and it's in simple harmonic motion, and we want to know the period. So from our formula sheet, we know that x equals a cosine times omega t plus phi. And then I won't go into the calculus, but due to some calculus, if you take what's called the derivative of x, which is essentially how x changes in time, which if you think of what velocity is, it's meters per second. So if we think of how x changes in time, we call that dx over dt, then it makes sense that that would be also in meters per second if you think about some, distance being moved over some time. So the velocity we have as negative a times sine, we have an omega in here, times sine of omega t plus phi. And then the acceleration which is really the rate of change of the velocity over time. So you take the derivative, which is not important for you to know, of x to get v. You take the derivative of that to get a, as v is the rate of change of x and a is the rate of change of v over time. And we have in our formula sheet here that the acceleration is equal to negative a omega squared cosine times omega t plus phi. Now, if you recall from your unit circle, both sine and cosine are functions that no matter what is in these parentheses, we'll call it x, in this case it's omega t plus phi, they both have a maximum value if you think of, here's the sine function, it's graphed like this, and right here is 1, right here is negative 1. They both have a maximum amplitude value of 1 or negative 1. So the velocity here is going to have a maximum value whenever this sine equals 1 or negative 1. So we'll just assume negative 1, and we'll say that V max equals A times omega. And similarly for the acceleration, it's going to have a maximum value when this cosine function equals 1. And the reason that is simply because if you're anywhere in between these 1 values here, then this is going to be like, we'll call it maybe pi over 2 times a omega, which is smaller than simply 1 times a omega. So the maximum value is going to be a times omega for velocity and a times omega squared for acceleration. So what we can do with this information is, again on our formula sheet, we know that omega is equal to a max divided by v max. And really that comes from if I do a omega squared over a omega, these a's cancel out, and you're left with 1 omega on top, and that just equals omega. So in this case, we have 5.0 meters per second squared over 4.0 meters per second equals omega. That equals 1.2, but we also know that that's going to equal 2 pi over t. And that simply comes from, we know omega equals 2 pi over t from our formula sheet. So if I were to multiply both sides by t, then I have 1.2 t equals 2 pi. And then if I divide both sides by 1.2, then I have t equals 2 pi over 1.2. And when I get that, we get 5.03 seconds. And that is option choice D on our sample test here. So that's how we solve this one. There's some weird nonsense in here. This is all optional for you to dig into, to understand. If you prefer, this is what you'll see on your formula sheet. I mean, you may see this, but you'll understand that Vmax and Amax are simply when this goes to 1 and when this goes to 1, due to the functions that, cosine, which is this one, and sine, which is the one I had already drawn, the way that they work. And as long as you understand that, then you can sort of logic this problem out. But all this will be written on your formula sheet. So we'll move on to number 8 next. All right, so now we're on to number 8. So we have two simple pendulums, and we're given their length. The length is equal, and the pendulum A has a period of t, and we're asked what pendulum B's period is if it's twice as heavy, or if it's actually half as heavy. So omega, we know, is root G over L for a pendulum. That's something that you should be given. But if not, this is just something that you should just remember. Going into detail on the derivation of this would be a bit complicated and involve a lot of calculus. So this is an important relation here. The angular velocity of a pendulum that's swinging back and forth is the square root of gravity over the length of the pendulum. We also know that the period is 2 pi divided by omega, or we can say, to parse it out here, 2 pi times 1 over omega. 1 over omega is just going to involve swapping the fraction here under the square root. It's just the square root of L divided by G. So this means that T is going to equal 2 pi times 1 over omega, which we have here as the square root of L over G. So in this case, L for we have the period for A is just T. We can call it T sub A, and that equals 2 pi times square root of 3 meters divided by G, 9.81. And then let's set up the period for B. This is 2 pi. This one's half as heavy, but it's the same length. So underneath the radical here, we'll have 3 meters divided by 9.81. And if you'll notice, you really could have even, noted it back here. This formula for the period does not depend on mass. There is no mass in this formula. So it's a complete red herring when he tells you that the pendulum A is twice as heavy as pendulum B. This means that the period of pendulum A equals the period of pendulum B, which we were given as simply T. And that being the case, the correct answer choice here is B. This one's pretty simple as long as you remember this right here. So with that said, we'll move on to number 9 now. Okay, moving to number 9. This is a Doppler effect one, which is always fun. So it's a car alarm that's going off, and you're on a motorcycle, and you've already passed the car, and it's going to have some frequency shift that's going to make it start sounding weird. And we've all heard that when we drive by some sort of loud noise. But it's asking how fast you must be moving on your motorcycle if the frequency shifts from 520 hertz to 490 hertz. And we know that the speed of sound is, of course, 343 meters per second as given. So when there is a source that's moving, the shifted to frequency, F prime, equals the original frequency times V over V plus the velocity of the source. But we're not using that one here. In this case, the motorcycle is moving. So the proper formula that you should remember is the frequency is going to equal the actual frequency of the source times the velocity that you're moving at, or it's going to be the velocity of the sound that's moving towards you minus the velocity that you're moving at, which we can call u naught, all over the velocity of the sound wave. All right, and essentially we just need to rearrange this to find u naught. So we can say f prime over f of the sound, frequency that you're experiencing divided by the frequency of the sound as it actually is being emitted. So we divided both sides there, and that would equal V minus U naught over V. And then if I multiply both sides by V, then we get this. And then if I add U naught to both sides and then subtract this part to the right hand side, then I get U naught equals V minus, or we can even say V times 1 minus F prime over Fs. And that simply comes from V minus V F prime over Fs, and this equals V times 1 minus F prime over Fs. So that's where this little part comes from on the right hand side. I simply distributed. So now that we have our formula rearranged, we can start plugging and chugging. So in this case, we're going to have U naught equals the velocity of the sound wave, which is 343 meters per second. And then all of that times 1 minus the frequency as you're experiencing, which is 490 hertz, divided by the actual source frequency, which is 520 hertz. And this is just going to be equal to 343 meters per second times 1 minus 490 divided by 520, which, let me do a quick calculation here. 490 divided by 520 is 0.94. This is 343 meters per second, all times 0.06. And this is going to equal roughly 19.8 meters per second. And that is answer choice. Well, it equals, in this case, around this number actually, 0.06, when you multiply that by 343. When I actually calculate it, it gives me like 20.58. But I got that 0.06 from this 0.94 here, subtracting 0.94 from 1. And this is actually a longer decimal. When you plug this into your calculator, you'll be doing 1 minus some other number. And when you multiply that number by 343, you should get something closer to this 19.8 value. Regardless, when I look at my answer choices, if I am taking a test and I do get 20.58, a really good practice to get into is I look at my answer choices. I trust my math. I trust that I'm using the correct formula. It's the only thing you can do. That's what you should do on your exam. You should trust your math. What's the closest value to this 20.58? Well, that's C, 19.8. It's only like 0.8 away. This 22.3 is also close, but you're 1.8 away or 1.7 away. So it's much better to go with this C here. And always trust your math. But when you actually plug in what this decimal right here actually is to this formula, you should get something closer to 19.8. So yeah, that's number 9. We'll move on to number 10. All right, so we have number 10 here. And we have the intensity level of one trombone is 70 decibels, and we want to know what the intensity level of 76 trombones is. So we have this formula in our formula sheet. It's not important to know where this formula comes from. It's complicated math behind it that you don't need for this course, but it's given on your formula sheet. So this I here in this beta, which is the decibel level, equals 10 times the logarithm of I over I naught. This I is some intensity that has to do with the actual level of sound that you're hearing. It has to do with this trombone. This I naught is actually kind of interesting. It's a reference intensity of sound, and it's actually the smallest sound that the human ear can hear. So that's how they chose this formula. it's all sort of arbitrary. There's no real deep physical meaning to it like there is with a lot of this stuff. When sound engineers were coming up with how to measure sound intensity, they simply chose the lowest intensity possible as a reference intensity, and then related that to some intensity of whatever they're measuring. And then they used mathematics to realize that you could just get a logarithm to sort of get a nice scale. But anyway, this is the formula we have. We know that the intensity of 76 trombones is going to be 76 times the intensity of one trombone. So, essentially, if I say that we have the total sound intensity that we're looking for here, then, what we're going to be looking for is essentially 10 times the logarithm of 76 I over I naught. Just plugging this in for, this we can think of as beta of 76 trombones. And we would use I-76 here, which is simply 76I. Now, the way logarithms work, if I have the logarithm of x times y, this is actually equal to the logarithm of x plus the logarithm of y. And similarly, the logarithm of x divided by y is the logarithm of x minus the logarithm of y. So this is a very important property in general. And, wow, that was hideous. All right, very important property in general, and it's very important for this problem. I'm not sure if you've learned this properly in your pre-calculus courses. I don't remember when you learned it, but essentially, we can exploit this property to say that beta of 76 trombones is equal to 10 log of 76 plus 10 log of I over I naught. But we know that this value right here is simply equal to our original beta of one trombone, which we know to be 70 decibels from our problem. So really, this equals 10 log 76 plus 70 dBs. And that is equal to our sound level of 76 trombones. And you really just plug this in your calculator, and you'll get that the sound intensity of 76 trombones is equal to this value, which I have as 18.8 plus this value, which is 70. And that obviously equals 88.8 decibels. So this is your sound level of 76 trombones. And we see that that most closely correlates on our answer sheet with option number A. So yeah, that's number 10, and we'll move on to number 11 next. Okay, so now we're moving on to number 11 here. And we have a 60 centimeter long string with a mass of 8 grams, and it has a tension of 200 newtons. And we want to know the fundamental frequency, which we can think of in this context as F naught of this string. And you should be given in your formula sheet that this is equal to 1 over 2 times the length times the square root of the force due to tension, F sub t, over mu. And what mu is the it's the linear mass density of the string. So essentially, if you have a string, it's the density of mass of this entire string. So it's actually m over L instead of m over v. We usually think of density as rho, m over v. That's in 3 dimensions. like the board we were talking about in the other problem. In this case, we're thinking linear mass density. Linear meaning only in one dimension, x dimension. It's in a straight line. So this is how we think of linear mass density. So, yeah, we have this situation here. Obviously, in our problem, we are given the length here. We are given the mass, and we are given the tension force. So it is beneficial to us to rewrite this F naught in terms of the variables we have. So we have our length, so we can keep this as 1 over 2L. We have our force due to tension. We don't have a linear mass density, but we can calculate it by simply calculating M over L. And if we just plug this in here, we can think of this as Ft over mu equals Ft times 1 over mu. And 1 over mu would just be, taking the reciprocal of mu here. It would be L over M. So we can think of Ft times 1 over u as equaling Ft times L over M. So we can put that under the radical here. Once we do this, we can simply plug and chug here. I mean, we've got 1 over 2 times 0.6 meters. Always remember to convert your units. And then under the radical, we've got 200 newtons times 0.6 meters all over that 8 gram mass. But in this case, we want to convert to our base mass unit, which is kilograms. Move it over 3 decimal places. We've got 0.008 kilograms. And when I do all this calculation, we get 102 hertz, which is the unit of frequency. And as you look through our answer choices, that corresponds with with letter D. So that's number 11, and next we'll move on to number 12. All right, so now we've got number 12 here, and this is an interesting one where you're thinking about a real-life place. We're thinking about the Mariana Trench in the Pacific Ocean, which is incredibly deep. It's 11,033 meters. It's astonishingly deep. And we know from our formula sheet that if we want to calculate the gauge pressure, which is what it's asking for of water at this point, then we use the gauge pressure is equal to the density rho times the gravitational acceleration g times the height h. But this is one where it actually is useful to derive. If I think of a slice of this water, if I have this entire, let me draw it this way. If I have an entire body of water and it's in a pool, we're not thinking about Mariana's Trench anymore, we're just thinking about a pool of water. And I have this slice of the water, right? And I want to just evaluate the pressure that this slice is exerting. Well, let me just go a couple places and then I'll tie it all together. So it's apparent to me that if I want to take the volume of this slice, if I have the area of this two-dimensional slice, or even of, let's say, the area of this little chunk of the slice, and then if I were to, continually layer the chunks on top of each other, eventually what I'm doing to get the volume of this slice is I'm multiplying the area, which A is the area of this little chunk, times the height. If I multiply the area of this little slice times the height of this column, then I will get the volume of this column. Okay? You can geometrically reason that in your head. You can spend time trying to think through what I'm telling you there. You can, have a few different tools explain that to you. You can ChatGPT would be useful, but if you wanted to take my word for it, you can do it that way too. If you multiply the area times the height, you get the volume. Now, we know that the pressure exerted by this water column is going to be the force over the area. That's the fundamental truth of what pressure is. It's force per area. The less area I'm applying a certain force to, the more pressure I'm applying to that certain point. It makes sense. If I push my finger onto my arm, then I'm going to experience more pressure on my arm than I would if I were to press my whole hand on my arm at the same force. So the smaller the area is, the larger the pressure is, and the larger the force is, of course, the larger the pressure is. But that's what pressure is. We know that this is fundamentally mg over A. And we know from the problem we worked in our earlier tutoring session that one way we can actually express m here is by saying it's equal to, we have rho equals m over v, therefore m equals rho times v. So we can say this is equal to rho times v times g over A. But if we set v of this column of water that we're analyzing equal to A times h, then this equals rho times A times h times g over A. Maybe now you can see where this is going. These two a's cancel. This equals rho times h times g. So the pressure of this slice of water and this slice, no matter what slice it is going to be this rho times h times g, and that's going to be derived from the same place for each individual column. So now we get back to just analyzing the body of water, and we know the pressure equals rho gh, and we can just plug and chug. So the density of seawater is 1025 kilograms per meter cubed times gravity, which is 9.81 meters per second squared, times the height, which is the depth in this case. The height here, as I count up this column, it doesn't matter what direction you're going in. The depth is going down, the height is going up, but either way it's going to be 11,033 meters. So, yeah. And when I do this, my final answer that I get is 1.11 times 10 to the 8th pascals. We have kilograms base unit, meters base unit, meters base unit, so this is just in pascals. And our answer choices here are in pascals, and the one that corresponds is letter D. So that's number 12. Hopefully this derivation helps a little bit. And if it doesn't, you don't have to know it. You can go into your test just thinking about this formula that will be on your formula sheet, but it might help you internalize what's going on here. And now we'll move on to number 13, which we'll cover very briefly since we went over it in our tutoring session. Okay, number 13. So I have both the non-answer key version and the answer key version up here because I wanted to show you something I think may have been confusing you when you were going through this, and it may have needlessly confused you. So your professor, it seems, may have made a mistake here. If you look over here in the answer key version, we're given the dimensions of this board. We talked about this problem in detail over our tutoring session, and we know that we need the dimensions in order to calculate the volume of this object. But if you actually look here, this is where that should be, and where we start this problem is over here in the answer key. We don't get the dimensions at all. It would be impossible to solve this problem over here with the information given. So that may have been what confused you. You know, I don't think it's necessary to go over the problem again. I think you got a good understanding of it from our tutoring session. Obviously, we set the weight of the board equal to the buoyant force of the water. We can then, in the same way that we did in the last problem, set m equal to rho, the density, times v, and then times g here. And then here we can set this equal to the density of the water times the volume of the displaced water times g. And then you just plug and chug, do your math. The g's cancel. This is how you get the volume of the displaced water, which is equal to the volume of the object within the water. And as we went over in the tutoring lesson, you end up getting this 0.7. And so that's what you would get if you had enough information. But I just wanted to quickly show you that that may have been why you were confused as well. So yeah, that's number 13. We'll move on to number 14 now. Okay, number 14 here. So we have a 4 kilogram cylinder of solid iron, and I'm going to draw this problem out the way your professor did on his answer key. I think it's a very useful way to think of this. We'll just do this as my rough approximation of what a cylinder looks like. It's on a string, and we can just imagine it's like attached to a wall or something, or a ceiling, I guess. And it's being submerged in a little bath of water here. And there's the water. So we know that the object obviously has some weight, mg, that's one force. We know that this string has some tension applied in this direction. And we know that obviously we have a buoyant force from the water. Now, this cylinder is not moving up out of the water. It's not sinking down any further. It's being supported by this string, and it's perfectly still in place. The fact that it's perfectly still must mean that the upward forces are equal to the downward forces. There are no horizontal forces to consider in this problem, so that's all we need to say. And we can simply say that the weight of the object, that force, is equal to the tension in the string plus the buoyant force. We know from what we derived during our tutoring lesson from problem 13 that the buoyant force is equal to the density of the water times the volume of the displaced water times gravitational acceleration. And if we rearrange here, then obviously T just equals mg minus rho water volume of displaced water times g. Right. And when we plug these in, we just get 4 times 9.8, 9.81, however you want to do it, but we can do 9.8 here, times 1,000, which is the density of water, which we can multiply by the volume of the displaced water, and we can do that as 4 over 7860. And really where that's coming from is if we know that density of the iron equals the mass of the iron over the volume of the iron, then we know that the volume of the iron equals, if we multiply by V on both sides, and then we divide by rho on both sides, this equals M over the density of the iron. So that's all we're doing here. We're given that the mass of the iron is 4 kilograms, which we put here. And we're given that the density of the iron is 7860 kilogram per meter cubed, which we put right here. And that just comes from this relation. So we have 1,000 times that, which is the volume of the iron, which is, as we discussed during our tutoring, the volume of this iron block here is going to be the same as the volume of the water that it's displacing. Those are always equal in these problems. And then we just have times the same gravitational constant that we used before. When we calculate this all out, we get 34 newtons, and that's going to be our tension force. So our tension force is 34 Newton, which corresponds with option D in our problem. This may have been a little strange with using this. This is, as in problem 13, something that is good to internalize, that the volume of the water that you're displacing by putting any object into the water is equal to the volume of that object. So yeah, that's number 14. And now we'll move on to number 15, and we're getting to the home stretch here of problems that are work driven rather than multiple choice. So yeah. All right, so now we're on to number 14 here. And it's set up as a pulley system where we have some disc that the pulley depends on, and then we have a block of mass m, which is 1.4 kilograms, and we want to drop it some height h. It doesn't matter if it goes all the way to the floor or not. Well, actually, in this case, yeah. We're going to assume that it's going to the floor, regardless. It drops some height h here, and this radius is r. So, in this case, we're simply going to say that the initial energy is equal to the final energy. That's how we want to try to use some algebra to find the velocity. Our initial energy, we know that the block is at rest. The block is at rest and it's some height off the ground. That should clue you in that we're just dealing with potential energy at the beginning here. So we have some mgh here, m being the mass of the block. And then the final energy, we know that this block is going to move down here. And that's going to give us some translational kinetic energy, which we know always equals 1/2 times the mass of the object times the velocity squared. So we have that component. But some of this potential energy actually goes, we have an entire system here that the energy is conserved in. And some of this potential energy at the beginning is actually going to be transferred into this pulley system. Otherwise, this disk wouldn't spin at all, and this mass wouldn't be able to fall. Some energy has to allow this disk to rotate. So we have to account for that when we're setting up our final energy here in these sorts of problems. And we know that this is going to be a rotational kinetic energy. And that always equals 1/2 I omega squared. Again, seeing that sort of equivalency between the rotational form, I being the mass, omega being the velocity. So we have 1/2 times the moment of inertia times omega squared. Now in an earlier problem, I showed you a hoop or a mass on a rope that's being swung around in a circular path. And I told you that I just equals mr squared. Now this is the simplest possible mass distribution in a rotational form. So the mass is just all along the rim of the circular object here. And that's the only thing that's spinning here. So we have a real simple mr squared. And since this I has to do with some mass, it's sort of a rotational equivalent to mass. If we have a solid disk now, which is what we have in this pulley system, there's more mass here. So if I take away the way that I colored this in here, but this is still a solid disk here, we have mass on the rim that's rotating. We have mass inside that's rotating, mass in here that's rotating, mass in here that's rotating. So obviously, this number that is the equivalent to mass should go up. We have more mass that's being, and this should be some m, capital M here to differentiate it from the block. But we have more mass that's being rotated around here. So, they worked this out. You'll get this on a formula sheet. You don't need to know how to derive this. But for a solid disk, I equals 1/2 times m times r squared. So we have this coefficient of 1/2 out front to account for the mass that's all around. So this is going to equal 1/2 mv squared plus 1/2 times I, which is 1/2 capital M r squared, times omega squared, but we know that omega equals v over r. So this is going to be v squared over r squared. These two r squareds cancel, and this becomes 1/4. So if we set these equal to each other, we have mgh equals 1/2 mv squared plus 1/4 capital mv squared. All right. Essentially, we can now go ahead and start to isolate v. So we have mgh equals 1/2 v squared times m plus 1/2 capital M. So then we have 2 mgh equals v squared times m plus 1/2 capital M. Therefore, we have that 2mgh all divided by m plus 1/2 capital M. If we divide by this part on both sides, equals v squared. And then to isolate for v, we can just say take the square root of both sides, and v equals 2mgh divided by m plus 1/2 capital M. Now I did a slightly different algebraic manipulation than your professor. I took it a little bit further. He took it to right here, I think, somewhere around there. Except I don't think he multiplied by 2 on both sides, but regardless, he took it somewhere around this step, and then he just kind of said, okay, v must equal this. But this is the in-between that he didn't show. This is how you isolate for v. Now we have our v isolated for. We can just plug and chug. V equals square root 2 times the mass of the block, which is 1.4 kg, times gravitational acceleration, which we can use just 9.8, times the height, which we have here listed as that 0.5 that it's dropping from. And then we have the mass of the block, 1.4 kilograms, plus 1/2 times the mass of this disk, which we have as 0.31 from the problem, kilograms. All in all, when I plug this in, we're going to get this equal to roughly 2.97 meters per second. And it's, that's what your professor got there. You can calculate this for yourself to see how close it is. If there's some variation between this 2.97 and what this answer is, it shouldn't be much. And you'll get full credit for something like this. Even if, don't be too afraid if you're on your test and you end up getting like 2.93 meters per second or something like that. Like, you're going to get absolute full credit for that. So these sorts of problems, there's more leeway with the number that you actually get. But yeah, that's problem 15. Now we're on to the final two, starting with number 16. All right, now we're on number 16, the penultimate problem here. So we're really just given a wave function here. We know y of xt is equal to the amplitude times cosine times kx plus omega t. That's the formula that's being shown here. And we are asked to show the amplitude, which is right here. We are asked to show the period, which the period is 1 over the frequency, is how we'll gain it here, knowing that omega here equals 2 pi times the frequency. That would mean that the period, as we've mentioned before, is actually 2 pi over omega. So in this case, we could simply say this is equal to 250. We have a pi in there, so it's going to be pi times pi, or pi squared. Or, excuse me, so sorry. This should be on the denominator, but we do have a 2 pi on top. This t is equal to 2 pi over omega, which is 250 pi. These pi's cancel, and this is just 2 over 250, or 1 over 125. And that's going to equal 8. And I guess they want it in milliseconds here. I suppose really this is going to be something like 0.008, which is you can rewrite as 8 milliseconds. This is in seconds here. Obviously, from before, amplitude is simply just this part right here. This is just 0.75 centimeters. And you can answer the problem this way. It looks like he doesn't have a problem with that. So we have our amplitude and we have our period. Now we want our frequency here. So the way that we can get that is if the period is 1 over frequency, then the frequency, if we multiply both sides by frequency, then we have ft equals 1. Then we divide both sides by t, we have f equals 1 over t. Our t is 0.008 seconds. In this case, we can really just say that it's 1 over this number here, because t is equal to 1 over 125, which just happened to equal 0.008 seconds right here. This 1 over 125 was equal to t. When we do 1 over a fraction, we just take the reciprocal. So that means that f equals 125 over 1, which is just 125 hertz. So I'm going through a slightly different way than your professor did of deriving some of these, just to show you there's many ways to sort of, attack this problem. The wavelength here, we know that wavelength, well, we know k equals 2 pi over lambda, with lambda being the wavelength. That's something you should get on your formula sheet, or something that's similar that you can rearrange into this. Therefore, lambda, if we multiply both sides by lambda and divide both sides by k here, equals 2 pi over k. Now we know k from our problem here is 0.4 times pi. So this is 2 pi divided by 0.4 pi. The pi's cancel, and we just have 2 divided by 0.4, which is going to be 5 centimeters in this case. And this is not from a conversion. This just comes from the fact that we have a centimeter inverse right there. So this is in units of centimeters, just from the way the problem is set up. So that's what lambda equals. So we can start circling some of these. And now we have the wavelength. And the speed of propagation is just the translating velocity of the wave. It's how it moves from left to right. And we know from our formula sheet that that equals lambda f, the wavelength times the frequency, which we've already gotten from previous parts of the problem. We can use meters this time since we want this in meters per second. So 5 centimeters is 0.05 meters. And then we want the frequency, which is 125, and it's already in base unit of hertz. And when I do this, I get 6.25 meters per second equals V. So now we have all 5 of the properties we were asked to attain, and it's pretty simple to get these just from the wave function that you're given. And this is the way I got it. Your professor got it a slightly different way. Hopefully both are instructive to you. That's number 16. Now we're on to the last problem, number 17. All right, now we're on number 17, the hardest one. So it's always fun how they do the hardest one last when your brain's tired, right? But alas, that's what they do. So we're given a horizontal pipe, and when we have a larger section of the pipe with a diameter of 3 centimeters, or this is actually the diameter, so that should be the whole thing anyway. We have a flow rate that's given, and then this sort of constricts down to a smaller pipe, and it's flowing this way. We know from the continuity equation of fluid that the area of the first section right here times the velocity in the first section equals the area in the second section times the velocity in the second section. That should be on your formula sheet. Where this actually comes from is if you think of like the flow rate of water through here, we can call it Q. That equals A times V. And the reason that is, and V being velocity, if you think of the flow rate, the volume flow rate, as being meters per second times some area, the reason is because you have some volume or velocity here that the water is moving in at the beginning. And then at every moment in time as it flows through, it's flowing through some circular cross section of the pipe that has area A. So that's sort of why we're counting the velocity at each little circular cross section by doing A times V. That's where this flow rate comes from. And the flow rate at the beginning of the pipe here is going to be the same as the flow rate at the end of the pipe here. And that's simply how fluid mechanics work. It's not important to know why, but Q1 equals Q2, therefore A1 V1 equals A2 V2. So we want to find V2 if we're given V1. Well, we know A1 is just the area of a circular cross section of this section. So it's going to be pi r squared. In this case, it's going to be pi times d over 2, which is r. R equals the diameter divided by 2. And it's d over 2 squared, which is just going to be d squared over 4. d1 squared over 4, since 2 squared is 4 here in the denominator. And A2 equals pi d2 squared over 4 then. And if we're isolating for V2 here, then we can divide by A2 on both sides. And that's essentially what we need to do to isolate for V2. So V2 equals A1 over A2 times V1, or A1 V1 over A2, but I'm going to write it this way. So A1 over A2, which is what we need to find to get this part right here, is equal to pi over 4 times d1 squared divided by pi over 4 times d2 squared. These pi over 4's cancel, and this equals d1 over d2 all squared. So that's what A1 over A2 equals. So we have V2 equals d1 over d2 squared times V1. And when we plug these in, we're just going to get 3 centimeters, or 0.03 meters, divided by, it was, I believe it's not written right here, but we should have, yeah, okay, well, it looks like your professor forgot to put the diameter of the narrower pipe, but on his solution set, sort of like in problem 13, he does have it, but this is going to be 0.025 meters, and this is all squared. And this is all going to be times V1, which is 1.5 meters per second. And when you calculate this whole thing out, I get 2.16 meters per second, which looks like that's what your professor got as well. Now, for part B, what we want is the pressure in the narrower region. So in this case, we know that the pressure at the beginning also equals the pressure at the end. And really, or it's actually the equation in your formula sheet, the way it's written is pressure 1 plus something that is probably accounting for how these volumes or velocities change and stuff, is equal to pressure 2 plus that same factor with the second volume. And so if we want P2, then we simply do P1 plus 1/2 times, or really times rho, all times v1 squared minus v2 squared. And that just comes from if we subtract this term and put it over here, minus that, then we have a 1/2 row in common on both. So I just distributed that right here. And then here we have a v1 squared. Here we would have a negative v2 squared once we move it to the left-hand side. So that's where this comes from. So P2 then equals, in this case we are working in kilopascals from the very beginning here. That's the unit they give it in. You can convert it to pascals if you want, and you will get this problem 100% correct. Your professor should not have a problem with that. He won't have a problem with that. But it's easier just to work in kilopascals if it looks like he's okay with that. So we'll do 5.21 kilopascals plus 1/2 times rho, which is the density of water. So 1,000 kilograms per meter cubed. And then we already have our velocities, 1.5 meters per second squared. And that's minus our velocity from this part, which is 2.16 meters per second squared. All right, that's our pressure 2. And when I calculate that all out, I get 4.0 kilopascals, which is what your professor gets. Whoop, that was an ugly square. Got to end on a strong note here. That's what your professor gets as well. So that's where that comes from. If you want some more detail on deriving this, like I sort of gave for this right here, then go ahead and ask me for it. But it is a little bit more complicated. There's not as much calculus as some of the other ones where I said it's completely useless to derive it, but it's a bit complicated. So this should be on your formula sheet, and you shouldn't need to derive it. But yeah, that's number 17, and that concludes the entire exam review. So hopefully this was helpful for you. In the morning, I'll go through and put some timestamps in for where each problem begins to kind of help you navigate this. But yeah, hopefully it's helpful.